Hello friends, now today we will do chapter number 6, principal stresses and strain. Principal stress and strain. Right, in earlier lectures we have done 5 chapters. Right, now from today we will do chapter number 6. So very first point in principal stresses, if I have an element in which the normal stress is applied in this direction, sigma x, sigma y, right, and I want to calculate normal and shear at this plane, which is anti-clockwise angle with the vertical theta, right? So the sigma theta will be, we have earlier discussed, sigma theta is sigma x plus sigma y by 2 plus sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Now tau I have not represented, this is tau in anti-clockwise direction, tau xy, right? This is anti-clockwise, here I will get a clockwise, and here anti, and here again clock. So this is the value of normal stress. Now shear stress I want, then just differentiate it. So what I will get, minus sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta, right? So this is the shear stress and this is the normal stress at this plane, and sign convention is very important, right? Now second point, on x and y phase, the x and y phase are called complementary planes. Complementary planes, or you can say faces, right? If they are complementary, then the value of sigma, that is sigma x plus sigma y, is always constant, right? What I mean, if I have a body and this is y phase and this is x phase, and if I move at some angle, so this is y phase, and if I am taking any other x phase, let us consider x dash, and any other y phase, that is y dash, then sigma x and sigma y will be, this is basically x and this is y, so sigma x dash, sigma y dash, right? So what is sigma x plus sigma y is equal to sigma x dash plus sigma y dash, right? So this is called complementary plane condition, right? And in this only you should know one more thing, that is tau xy will be equal to tau yx, right? Tau xy, here you can see tau xy and this is tau yx, so they are equal to each other, and the value of tau yx is minus tau xy, right? Now next, third point, hydrostatic condition. Hydrostatic, see, if we have a container and the liquid is in static condition, so here only sigma is being acting, that is sigma y, and tau is 0. So if I draw its Mohr circle, sigma minus tau, this is plus sigma and this is minus sigma, this is tau, so I'll get what, negative sigma, so it is something here, it will be a point. Now so this is called analytical approach. Now we will do graphical approach. Graphical approach, that is Mohr circle. Mohr circle, right? Now let us consider a situation, sigma is 150, tau is 40, right? And here also we have sigma and tau, but the tau is clockwise, so this is my A phase and this is my B phase. So what I'll write, the coordinate of A, sigma comma y, that is 150 comma 40, and what is the point B? B is sigma is positive 150, but tau is in clockwise, so minus 40. So just draw this point on Mohr circle, sigma minus tau and tau, right? Now what is 150 comma 40? So 150 something here, 150 comma 40, so this is A, 150 comma 40, and this is B, 150 comma minus 40, and taking this as dia, draw a circle. So this is a circle, and here this is called sigma average comma 0. Now two things you should know, sigma average is called sigma x plus sigma y by 2, and radius the radius is given by under root of sigma x minus sigma y by 2 whole square plus tau xy square, right? So these two are important things. Now if I talk about one more point, that is, this is called maximum sigma, maximum sigma. So this is maximum sigma 1 and this is sigma 2. This is maximum sigma and sigma 2 is called minimum sigma, right? And here we are getting maximum shear. This is the condition for tau max, and at tau max I am getting sigma average, right? So you should know, at the point at which we are getting maximum sigma is called principal plane. Principal plane. Sigma 1 comma sigma 2 is called principal stress, right? This is A point. B, two principal planes are perpendicular to each other, but in Mohr circle the theta is 180 degree. Clear? And C, plane of shear S1 and S2 is maximum shear stress plane, right? If I talk about shear plane, this is theta 1, shear plane 1, theta S1, and this is theta S2, right? So theta S1 is what? Theta P1 plus 45, right? Because this is theta P1 for us, right? So theta S1 is something like this, and similarly if I want to write theta S2, it will be theta S1 plus 90 degree. Clear? Now see very carefully, fourth point. So that much you should know in Mohr circle, right? Other things you can just calculate from here, like this is the radius, this is the radius which I have written, and so on, right? You can calculate the dia, just half the dia you will get the radius, right? And the radius is tau max, all that things, right? Now let us move forward. Fifth point, for pure torsion, the shear stress, the principal shear stress will be 16T by pi d cube, right? It is very simple. This is the formula. And now the sixth point, if I am having a combined loading, like I am applying a moment, bending moment and torsion, right? So, then we have sigma max will be sigma maximum, right? So what I can write sigma maximum, it is 32 me upon pi d cube, right? And tau maximum, this me is very important, right? Me is called equivalent bending, equivalent moment. So me is calculated by, it is moment means bending moment. So it will be what? It will be m plus under root m square plus t square upon 2, right? So this is bending, equivalent bending moment. Now I am talking about torsion. So tau max will be, tau means torsion, 16 will come obviously, 16 te upon pi d cube. So this is the condition for torsion. And if I want te is torsion, just take this part. Torsion will be under root m square plus t square, right? So this is the condition, equivalent maximum normal stress, maximum shear stress, right? And if I want, next point 7, if I want to design a shaft, so if I want to design a shaft, so tau max will be max of sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, and sigma 3 minus sigma 1 by 2, the maximum of it, right? So here I am using MSST, maximum shear stress theory, right? I'll make theory of failures, I'll make a separate video on it, right? There we will discuss all the theories. Just I'm using here MSST, maximum shear stress theory. So maximum of sigma 1, basically sigma is what? As we know, this is sigma 1, this is sigma 2, and this is sigma 3. Just I'm using that, right? So these all are the condition for maximum shear stress. From here you can just calculate, this is basically tau 1 2, tau 2 3, tau 3 1. And MSST is used for ductile material. This is used for ductile material. Clear? From here you can calculate your tau max. This is for design criteria, otherwise you can use the direct result, this one. tau is what? 16t e by pi d cube, 16t by pi d cube, and t is what? Under root m square plus t square. Similarly, in equivalent normal stress, 32 me upon pi d cube. Just me, replace me by m plus under root m square plus t square by 2. Clear? So these two things are given to us. Now this is all about principal stresses and strains. Now I'll discuss the next chapter, that is chapter number 7, spherical and cylindrical pressure vessels. Right? So spherical and cylindrical pressure vessels. I'll discuss this. Now see very carefully. The first point, very simple. If I have a sphere and it is filled with a liquid, right, and the inner radius is r and the pressure exerted is P. So simply I want to write longitudinal stress. It is what? PR by 2T. Simple. PR by 2T. Right. So this is what? This is our axial stress. Axial stress. Now I want to write axial stress means stress in x direction. X direction. And if I want hoop stress, that is in y direction. Right. So hoop stress is sigma y, that is sigma hoop. It is the same, PR by 2T. Right. And what is T? T is basically the thickness of this shell. Thickness. Clear? If you have calculated sigma x, sigma y and sigma z, if we have sigma x, sigma y and sigma z, we can calculate epsilon x. It is sigma x by E minus mu sigma y by E. Right, we don't want sigma z, right, because it will be 3D analysis. That is not in our syllabus. Right, so this is strain in x direction. Similarly, I can write, because I have sigma and E is the material property, just put all the values, you will get the strain in x direction. Strain in y direction is what? Sigma y by E minus mu sigma x by E. And just moving forward in this, I can write the strain, volumetric strain, that is epsilon x plus epsilon y. Either you can do this or you can do change in volume per unit original volume, and change in volume will be what? See, if I just do a simple calculation, volume of sphere is 4 by 3 pi r cube. If I want delta V, what I'll write? 4 by 3 pi 3 r square dr. Right, so just put it here, 4 by 3 pi 3 r square dr. And what is volume? 4 by 3 pi r cube. 4 by 3 pi, 4 by 3 pi got cancelled. R square, R get cancelled. So what is this? This is 3 delta R by R. So this is volumetric strain. This is volumetric strain. Now, if I want to design, so this is, you can take it as second point. Now we have the third point, design of this spherical vessel. Design of spherical vessel. So if I want to do the design, I am going to use MSST. So if I want MSST, so what will be MSST? And here sigma z is 0, right? So this is sigma x, that is longitudinal, sigma longitudinal. This is sigma y, that is hoop. So if I want tau, if I want tau absolute will be what? It will be maximum of sigma 1 minus sigma 2 by 2, comma sigma 2 minus sigma 3 by 2, and sigma 3 minus sigma 1 by 2. Just take it the mod, and after calculating, this is equation 1. And also tau absolute is what? Tau yield stress per unit FOS, factor of safety. So, just you can equate 1 and 2. Equate 1 and 2. You can find the thickness, the pressure, right, and the radius of the sphere. That's all, right? And also one important thing, if I'm outside the shell, then sigma 3 is 0, but inside the shell, sigma 3 will be what? Minus P. Then you will take sigma 3 as minus P, right? Because inside the shell, the pressure is being applied by the liquid, right? That's why sigma 3 is minus P, right? Now let us move on cylinder. Cylindrical pressure vessel, right? Now this is the cylindrical let us take, for example, I'm drawing a cylinder like this, and just we are taking the standard things. This is x, this is y, and this is z axis, right? So if I want longitudinal stress, sigma x, longitudinal is what? Longitudinal is same, PR by 2t, PR by 2t. And if I want hoop stress, that is sigma y, hoop, the hoop will be 2 times sigma x. Hoop will be 2 times sigma x, right? So that's why the sphere is weak in lateral direction, because the hoop stress is very high. Now if I talk about its design criteria, fifth, here also we can do 2 things. If I want analysis, I have 2 cases, inside and outside. If I'm inside, then sigma 3 will be minus b, and outside there is no sigma 3, so sigma 3 is 0, right? Outside is generally the condition outside comes, right? Inside will be very much complex. Now then we will do just 2 things. We will do what? The first, tau absolute I will calculate, because I have sigma 3, I have sigma x, and I have sigma y. As we have sigma x, comma sigma y, and sigma z, accordingly I'll calculate tau absolute as max of sigma 1 minus sigma 2 by 2, comma sigma 2 minus sigma 3 by 2, comma sigma 3 minus sigma 1 by 2, and I'll write another equation. Absolute will be what? It will be yield stress per unit FOS, right? So this is 1 and this is 2. You can equate these two, equate 1 and 2, and you will get your PPR, right? And from here we can move forward and we can write volumetric strain. It is delta V by V. Just I am telling you the formula for delta V, right? Just you will put it here, and by calculation like this you will get your epsilon V, right? So what is the volume of the cylinder? Pi by 4 d square L, right? And from here if I do delta V, what I will get? I will get pi by 4, first same like L same, and D का differentiation करेंगे, so 2D delta D plus again D square same, और फिर इसका करेंगे तो इसका कितना हो जाएगा? डेल्टा L. So this is what? This is delta V, and delta V को हम divide कर देंगे V से. Getting the point? Then I will get my epsilon V, right? So just we are calculating it further. See now I can write it as a 6 point. If I want to calculate epsilon V, volumetric strain, then it will be delta V by V, and volume is what? Pi by 4 d square L, and from this you can write simply, see this is very important, right? 2 delta D by D plus delta L by L. So this is the volumetric strain. Now I will calculate delta D by D and delta L by L, right? So this is what? D, diametral means it is hoop, and this is longitudinal means it is epsilon x. Now how we will calculate hoop? Now see very carefully, hoop is what? Now hoop, how I can write hoop? It is in y direction, so sigma y by E minus mu sigma x by E, right? And sigma z I am taking as 0 because I am studying outside the sphere. Similarly, how I will write this? This I will write sigma x by E minus mu times sigma y by E, right? Now just we will solve one by one both the equations. Now what is this? Now I am talking about cylinder, right? And this is x-axis, this is y-axis, and this is z-axis. So if I am talking about sigma x, it is longitudinal, easy, and sigma y is hoop, which is 2 times sigma x. Yes, this is the important point that I am going to use here. So sigma y will be what? 2 times sigma x, correct, by E minus mu sigma x by E. Just take sigma x common, sigma x by E. So what I will get? 2 minus mu. So this is the hoop stress, diametral stress, right? Now I am talking about longitudinal. In longitudinal, what I'll write? Sigma x as it is, sigma x by E minus mu. And what is y? Sigma y, hoop, that is 2 times sigma x by E. So I'll take common sigma x by E, I'll get 1 minus 2 mu. So this is the stress in longitudinal direction. Just you will put these 2 points here. Epsilon V will be what? 2 times sigma x by E, 2 minus mu, and plus sigma x by E, 1 minus 2 mu. Just take common sigma x by E, sorry, 2 2s are 4, minus 4 mu plus 1 minus 2 mu. What I am getting? Epsilon V as sigma x by E, 4 plus 1 5, minus 4 minus 2, 6, minus, this is what, 2 na, so it will be 2 plus 2 4 mu, right? So this is epsilon v. If you want epsilon v, you should know epsilon h and epsilon x, that is hoop and longitudinal stress. Just add them, you will get the volumetric strain. Similarly, in the sphere you can write the same thing, right? If you want this epsilon v, so what is the volume? 4 by 3 pi r cube. So what you will write, the epsilon v, 3 comes forward, 3 delta r by r. Just learn this, right? And similarly, if I want, in case of volumetric, so what is volume? Volume of cylinder, pi by 4 d square L. So just use d square and L. You will write 2 delta d by d plus delta L by L. And delta d is hoop and delta L by L is longitudinal, right? And just add them, you will get the volumetric strain. Now we have all the values, sigma x, sigma y, epsilon. So you can now what? 7. Design. Design is done on the basis of MSST, maximum shear stress theory, right? The things are same only. And that's all for chapter 7. Now we will do chapter 8.